Continue on physical chemistry, chapter 15, we're section 10 now. We're going to talk about equipartition of energy. Now there were three red flags in the 1800s that classical mechanics wasn't quite right. And one of these was heat capacity. So we have energy kinetic is 1/2 mv x, y, and z squared. So we have the x component, 1/2 x component of velocity squared, plus 1/2 times mass times the y component of velocity squared, plus 1/2 times the mass times the z component of velocity squared. Now we know that momentum is equal to rho is equal to mass times velocity. So energy, kinetic energy, is 1/2 times the momentum in x squared divided by mass, plus 1/2 times the momentum in y squared divided by mass, plus 1/2 times the momentum in z divided by mass. Now the equipartition principle, or the equipartition of energy, says the average value of each quadratic contribution to the energy is the same and equal to 1/2 kT for one molecule or 1/2 RT for 1 mole. Now remember, K is Boltzmann's constant. It's 1.38 times 10 to the negative 23rd joules per Kelvin. So for energy translation, we have 1/2 kT plus 1/2 kT plus 1/2 kT. That's x, y, and z. So we get 3/2 kT, or 3/2 RT. So for helium, the internal energy, the molar internal energy, is 3/2 RT. Because each direction, x, y, and z, is 1 degree of freedom. Now, the molar heat capacity at constant volume is equal to the partial derivative of the molar heat capacity, or the molar internal energy, with respect to temperature, holding volume constant. So we get the heat capacity of the molar heat capacity at constant volume is 3/2 R for helium. So heat capacity is one failure of classical mechanics. Now here's a graph that you've probably seen about 5 times so far this term. So this is a graph of the molar heat capacity at constant volume divided by R to get rid of the units versus temperature for carbon dioxide. Now the expected value, according to quantum mechanics, is 6.5 because it has the translational energy and then rotation and vibration. We'll talk about that later. But the point is that classical mechanics says it should be constant. It should be a straight line. There's no reason for it to change. But this black curve, the round curve, it shows that it changes. It starts out small at low temperatures, it gets higher and higher and higher and higher, and even gets higher than 6.5 predicted by classical mechanics. Now carbon dioxide is a linear molecule, but it does have rotation and it does have vibrations. So here we go. For carbon dioxide, a linear molecule, we actually have the formula 3n minus 5 times RT, and that's just for the vibrational energy. Now if we have a nonlinear molecule, then we have 3n minus 6 times RT. So n is the number of atoms in one molecule. So for carbon dioxide, the molar energy is going to be 3/2 RT. This is from the translational energy we already talked about, and then 3/2 RT for the rotational energies, and then 4 RT for the vibrational energies. So that gives us 6.5 RT, 6.5 RT. And notice there's no reason for that to change with temperature. So remember, if you have a linear molecule, rotation about the axis doesn't count. That's why it's a little bit different for linear versus nonlinear molecule. So the heat capacity at the molar heat capacity at constant volume is 6.5 R. So we get the molar heat capacity divided by R at constant volume is 6.5. Now the energy of translation, remember, is going to be just n times the average energy of translation. The average energy of translation is 3/2 kT per one atom. So remember, the root of this equipartition of energy is classical mechanics, Newtonian physics. Now for N2, another linear molecule, the rotation is still 2/2 RT but the vibration is 3 times 2 minus 5 RT, or 1/2 RT. See also handout figure 49. And that is all we're doing for section 10, and that's also the end of chapter 15.